concentration. Is the solution concentrated, unconcentrated? So if something is concentrated, we might say things like too sweet, too salty, right? Too sour. Versus if it's unconcentrated, we might say it tastes like, it tastes dilute, it tastes watered down, not enough flavor, things of those ideas. So if it's too sweet, too salty, too sour, lots of flavor for us. If it's unconcentrated, it's dilute, it tastes watered down, not enough flavor. We might say add sugar, add salt, right? But a lot of these ideas of how we describe it is based on personal preference. What is too sweet, too salty, too sour to me may taste just perfect to you or not be enough flavor. So we have to take the subjectiveness away. And so scientists have come up with different ways to represent concentration no matter how it tastes to us. And so the most common way to represent the concentration is molarity. And notice it kind of has that word moles in there. So molarity assigns a number value to express the concentration in the terms of the moles of solute dissolved in liters of the solution. So the idea is that as you increase that molarity value, that means we have a higher concentration because there are more moles of solute dissolved in the solution. The mathematical equation is listed on our table T. You don't have to have it memorized. You just need to know how to use it. So molarity simply equals the number of moles of your solute divided by the number of liters of the solution made. So the unit that you'll actually see, I'm going to just write an example, 2.5 molarity. So a capital M in our class stands for molarity, the concentration. What this means is that it's 2.5 moles per liter. So instead of writing a fraction, we now just write a capital M. So it means 2.5 moles of that solute in 1 liter of solution. That's what it means. So we could write that down. So there's 2.5 moles of the solute in 1 liter of the solution. So that's what it means. So I'm going to look at a couple of practice questions. So first off, it just simply says calculate the molarity. So capital M is our unknown. So capital M, we need moles of our solute divided by the number of liters of solution. So when we read through this, it says 5.5 moles of the solute. So we're given the moles of solute, and it says in 12 liters of the solution. So we are also given. So this is a really straightforward question. We're given all the information. So our correct numerical setup would be 5.5 moles divided by 12 liters of solution. So right here, correct numerical setup. So this would be our CNS. And if we need a final calculated answer, we would simply put it in our calculator. 5.5 divided by 12. And so your calculator is going to give you a lot of digits. So it says 4, 5, 8, and then a bunch of 3s repeating. If we're thinking about sig figs, okay, here we have 2 sig figs. Here we have 2 sig figs. So that means we would keep 2 of them. That would round off, round it up. So final best answer would be 0.46, and the unit is capital M. So this would be our final answer versus correct numerical setup. Okay, so let's take a look at the next question. Calculate the number of moles. So in this question, where it says calculate number of moles is our unknown of the solute present in 0.100 liters, and we're given a molarity value. Now, this molarity value means 2.3 moles in 1 liter per liter. So here we go. To set it up so we don't mess up units or the type of math, we just do dimensional analysis. So we have 0.100 liters, right? Times. Well, we want to get to moles, and we want to come away from liters. So we have 2.3 moles per 1 liter. So unit-wise here, take a look. Liter times mole divided by liters are gone. We're left with a unit of mole. Here, we're starting off with 3 sig figs. So our number of moles should also be recorded with a final answer of 3 sig figs. So when you put it into your calculator answer is going to be 0.23, but that's only 2 sig figs. So you have to think, you have to be smarter than the calculator. So final answer here would be 0.230 moles. So because this is leading zeros are never significant, trailing zeros are. So 0.230 moles to maintain sig figs. Next example. What volume? So our unknown here, what volume of solution, that's what we're solving for, is prepared if 0.55 moles of a solute, so we're given the number of moles of solute, to make this concentration. So we know it's 1.25 moles equals 1 liter. That's what it tells us. So let's start off with the number of moles. We have 0.55 moles. We want to get to liters. We want to be able to cross off moles. So it's 1.25 moles equals 1 liter. So in this question, the 1.25 goes wherever I put the moles in the fraction, and the 1 goes wherever I put the liters. So now when I put this into my calculator, it's 0.55 moles times 1 liter divided by 1.25. And I get a calculator answer of 0.44. 2 sig figs, so my measurement starts off with 2 sig figs, and my calculator naturally gave me 2 sig figs, so I don't have to think if I have to add a trailing zero or not. Unit-wise, mole times liters divided by mole, moles reduce, and I'm left standing with just a liter. So my final answer, 0.44 liters.